And are you following books after classes? These are two very pertinent questions. Yes or no? Are you following whatever I am saying? And are you going through books?
Yes, sir.
Yeah?
Yes.
Everybody?
Yes, sir.
Any questions you have from the last class? Any questions you have from the last class? So, as usual, I will start with a very short recap. And I would say that we were trying to indulge in a very new topic called grammars, right? A very new topic called grammars. And for the time being, we are keeping aside our 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 endeavors on machines, and we try to define a grammar formally with such a definition. Everybody can see my board, right? This is what I talked about in the last class yesterday. So formally speaking, grammar is a four tuple, and it has non-terminals, it has terminals, it has a set of rules that you apply, and how you apply rules, it doesn't matter. That is also what I told you, and there is a start symbol S. So grammar is essentially VTPS. So these four elements of this four tuple is capable of defining what a grammar is, and we suddenly took certain examples, and we started with known examples of any number of zeros and any number of ones, right? So we started with this language because there is a very known language
Hello, Abhishek.
with a very yeah yes yes hello yes Basu, hello
Sir, it's not
hello
me, sir.
yeah yes, what happened? Hello.
Hello, yes, sir, you're audible.
So you're audible, sir. I don't think it was Basu, sir. I think it was Sangam, sir. But he
Yeah,
actually has a little bit of a net issue, sir. That's why he's not being able to ask.
but there is no issue with my class, right now.
No, 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 sir. No, sir.
Okay,
It's
okay,
his net.
okay. Yeah. So what I mean is, I started with a very well-known example so that things become simple to you, and slowly we will get into complexities, right? So as of now, I started with any number of zeros and any number of ones case, and we know how to build a very simple epsilon epsilon finite automata, right? Like this, any number of zeros followed by any number of ones, and we showed we expressed it in a language form, and we expressed in a regular expression form, and we tried to have a grammar for this, right? So we defined that, okay, our V is we need only one single non-terminal called S, and we had a tree representation for that. And do you know what this tree is called? This tree is called a parse tree, right? This tree is called a parse tree, and we showed the example that a very simple grammar of the form like this suffices to generate our language of interest. So S goes to 0S, S goes to S1, and S goes to epsilon. These three simple rules are denote, these three simple rules is your set P, the set P of productions, right? So VTPS, V is the set of, I repeat once more so that there is no confusion. V is the set of non-terminals, and in this case, in this case, we have V is equal to your S only, right? T is the set of terminals that constitute the string at the last. So if you think of a tree, so all the leaves of the trees will be of 0 and 1. These are the elements of the string. P is a set of productions, and here it is P. We have three productions, P1, P2, P3. And we apply these three productions to generate any number of zeros followed by any number of ones, right? And then we talked about a special case of this language, and that is same number of zeros and same number of ones. This portion. We talked about this portion, right? And we told that we discussed that if I ask you to give a grammar, that generates only this black portion. That means equal number of zeros and equal number of ones. The previous grammar that was used for any number of zeros followed by any number of ones will not give you always the strings that have the equality. So for the equality, we proposed a grammar, very simple grammar, and the technique was that we thought about generating zeros on the left and generating ones on the right of a pivot point, right, of a fulcrum, and we can say that okay, this type of production rule is nothing but a middle recursion on the right. So s goes to 0 s1 is nothing but a recursion in the middle, and you recurse like this and generate equal number of zeros and equal number of ones, right? You always generate equal number of zeros and equal number of ones like this, and finally you put s goes to epsilon. So we had two grammars, and of different say, okay, let me repeat, not go through this board work. Let me repeat things so that it becomes easy. So we had a very important question in mind. So for any number of zeros and any number of ones, we represented with m and n, where both m and n greater than equal to 0, so that we can have epsilon. Very simple. So this is language L1 that has any number of zeros followed by any number of ones. There is a different language L2 that always has equal, right? 0 n 1 n is greater than equal to 0. And the grammar for this, we wrote the production rules of this grammar as so let me write g1 is v1 t p1 s, where v1 is s, t is 0 1, p1 is consists of three production rules. What are the production rules? S goes to 0s, S goes to S1, and S goes to epsilon, right? And S is the mandatory start symbol. So this was your grammar. The grammar that we use to generate, any number of zeros followed by any number of ones, right? And how did we apply? We apply production. So if this is production P1, P small p1, say, if this is production p2, if this is production p3, three members of the set p1. Why p1? Because we are talking about some grammar L1. So 1 is the index of this grammar, to make things simple, right? So how to generate this language? Any number of zeros, any number of ones. The number of zeros that you want to generate, you apply p small p1 that number of times. So apply small p1 m number of times, followed by applying small p2 n number of times, and followed by applying p3 only once. In this sequence, will generate m number of zeros and n number of ones, right? Do you agree? So how does the tree representation look like? It looks like, oh, okay, s goes to 0s, that is we are applying production p1 once. So the number of times we will apply p1 is exactly equal to the number of zeros. So if there are two zeros, let us start with a string 0, two zeros and a single one. So I will apply again 0s, and then I will apply s1, and then I will apply s goes to epsilon. So I'm applying production p1, small p1 two times. I am applying small p2 once, and I am applying small p3 once. So that is what I mean by this sequence. So this is a sequence of steps that you apply, and this is the parse tree. Very simple. So you should not have a full class on what a parse tree is. Please go through book and listen to me with an open mind. Right? Done. So my intention is not about this grammar. My intention is something else that will become very clear. So let us try to generate a grammar for this. G2 is for the equal case, right? So let it be V2, let it be T, because T is same in both cases, because T is 0, 1, right? It's a binary alphabet, and it should contain terminals from that binary alphabet. So 0 and 1. So I have kept T, and let it be P2, the set of productions of this grammar, and let S be the start symbol of this grammar, right? So what does the grammar look like? So the product, so V has S, and T is same as 0, 1, and P here has only two productions. S goes to 0, S1. I am intentionally keeping the recursion in the middle so that always when I apply this production rule, always I generate a 0 on the left and a 1 on the right. So the count of zeros and ones are always the same, as well as the order, right? So S goes to epsilon, and we apply. What do we apply? We apply, this is production rule P2, this is P2, right? So this is production rule P1 of P2, and this is production rule P2 of P2, right? So what do we apply? S goes to 0, S1. For example, you have an example string of 5 zeros and 5 ones, same number of zeros and same number of ones, because that is the problem that we started with, that is the language that we started with. So you have to just apply P1 5 number of times, like this: 0, S1, again 0, S1, again 0, S1, again 0, S1, and you have to apply this production once to complete the derivation, right? So what do you get? You get 5 zeros followed by 5 ones, and you collect the leaves like this. Any problem? Now my intention was to differentiate those two grammars. Now, as per our knowledge, we know that this is a regular language. We know that this language is regular, any number of zeros and any number of ones. But we also know that this language is not regular. From your previous knowledge of applying pumping lemma and proving, this language is not regular, right? But L2 language L2 is just a subset of language L1, right? Do you agree? Language L2 is just a subset of language L1. Equal number of zeros and equal number of ones is just a special case of any number of zeros and any number of ones. Got my point? Yes or no? Okay. So then what is this language? This is not regular, that you know. This is not regular. And this was regular. So what is this? Now we try to come to the definition of what is this, other than saying blindly that this is a context-free language. I want to enter into the topic in a different way altogether. So let us write the grammars again. Grammars means the grammar rules. So S was 0S, S goes to S1, and S goes to epsilon. And here the grammar rules were S goes to 0, S1, and S goes to epsilon. Now, looking to the grammar rules, we'll try to differentiate these two grammars into different classes in the most general form. So that I say that in the most general form has a very deeper meaning. But we see that this structure of representing the grammar that solves this problem, that generates this language, is quite hastily taken, and it has no specific structure. For example, in this production, the right hand side has non-terminal as the rightmost symbol, and in this production, the right hand side has the non-terminal as the leftmost symbol, right? So you cannot take a general decision on how the productions look like. So what I did was, in yesterday's class, I transformed this grammar. To another equivalent grammar that works like the same, and I just introduced another non-terminal called A. So now my V is S and A, T remains as 0, 1, and my production rules are S goes to 0S, right? S goes to epsilon, S goes to 1A, S goes to 1, A goes to 1A, A goes to 1. I transform, this is the same grammar. This one was the grammar, but I was not able to take a general decision on how the productions look like. So I transformed this same grammar to this grammar by introducing another non-terminal, and without any loss of generality, we can say that this is a full-fledged grammar that satisfied the VTPS condition criteria, right? Why? Because V is finite. By addition of one non-terminal doesn't make V infinite, right? T is also finite. P is also finite, and we have a mandatory start symbol S. No problem in there. But having written the grammar like this, we arrive to a specific structure. What is that structure? That every production, the right hand side of every production has a non-terminal as the rightmost symbol, right? Either the right hand side has a non-terminal like this. So how many right hand sides have non-terminals? This one has a non-terminal. This production has a right hand side, and that has a non-terminal as a rightmost symbol. This production has a right hand side which has a non-terminal as the rightmost symbol, and all others have only terminals. I will deal with S or epsilon in a more delicate case later on. So don't worry about S or epsilon right now. Okay. So the general structure is that if we say that, okay, the production rules are of the form alpha arrow beta, where alpha and beta are strings from V union T star, we can say that, okay, each of these alpha goes to this beta has a specific form, and that form can be said that, okay, mod alpha is less than equal to mod beta. The left hand side is always less than the right hand side. This is observation number one. Observation number two is not only that it is less, the left hand side is exactly one. You always have a one non-terminal on the left hand side, right? Right? And the right hand side can be a series of series of terminals like this. S goes to 1, A goes to 1. I'm generalizing. It can be series of terminals, or the right hand side can be a series of terminals. I'm writing in small, followed by a non-terminal if any. So if the right hand side has any non-terminal, it should be the rightmost symbol. So this is a general observation that we can have from this grammar, right? And from this grammar, what observation can we have? S goes to 0, S1, S goes to epsilon, right? So the general observation is, okay, mod of alpha is less than equal to mod of beta. Mod of alpha is equal to 1 specifically, and beta has no restricted shape. Beta can be anything. It has no restricted shape. So that I use the term restricted shape, I use it intentionally because I will use this term quite often while talking about grammars. So on the counterpart, the observation number 3 from the regular grammar, from the regular language, what we have is people are saying that beta should be like this or beta should be like this. So it's a restriction on how beta should look like. Beta is not free. Do you agree? Beta is not free. So you dictate terms that this is how beta should look like. But here you say that, okay, beta has no restriction. Beta can be anything. Got my point? Now remember, we are not concluding this. We are not concluding this in the most general way only from these examples. I'm trying to explain you that these examples follow these rules. It is not the case that from this example I derive these rules. It is rather the opposite. I'm trying to explain it to you that these are the general rules that every regular language, every regular grammar should follow. These are the general rules that every context-free language should follow. Got my point? And this is just an example. This grammar is just an example of such rules being imposed. This grammar is just an example of such rules being imposed. Got my point? Yes or no? Hello? Anybody there?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, understood?
Yes, sir.
Okay.
Yes.
Yeah, now if I say that this grammar has a name, let us give it a name. As you gave it a name, you gave it a name that it is a regular grammar. And you said that if there is a if there is a language, if there is a machine that generates a regular language, if L is regular, LR, then the machine generates a regular language. And that language is defined by M bracket LR, right? Similarly, this same language is generated by a grammar, right? A regular grammar. This is the same. So they immediately you see a machine to grammar correspondence. So a finite automata generates a language. Finite automata rather accepts a language that is generated by a regular grammar. So you have this correspondence. I'll talk about this correspondence later on, but let me come back to my point. My point was you had already named this grammar, right? You have already named this grammar because this was a regular language, and a grammar for a regular language that generates a regular language that generates the strings of a regular language is a regular grammar. So now let us name this grammar as context free grammar. Now that I say that this grammar is named as context free, there is a very natural question that should come, that if this is a context free grammar, there should exist something called contextual. Right? There should exist something like contextual. So if this grammar is context free, that means there should exist something called contextual, right? Otherwise, why you are calling this context free? You are calling this context free because there exists something that is contextual or context sensitive. And with respect to context sensitive grammars, you are saying that, okay, this grammar is context free. So there should exist something called context sensitive. It's a very similar analogy to your daily life. If I say that something is good, there should be something that defines what is bad. If there is no darkness, there is no value for light. Do you agree? If you cannot see darkness, and if you cannot compare darkness with light, light has no cognitive value, right? If it is not supported by darkness. So after all, it is all contrast. So when you name this grammar as context free, there should exist, common sense says that there should exist something that is contextual or that is context sensitive, right? And with this knowledge, let me say you that yes, there exists such um, grammars, and to denote such grammars in the most general form, I would rather use a Venn diagram. I will name it later on. I will use a Venn diagram, and I will classify the languages like this. Very simple classification. These are regular languages. These are context-free languages. These are context-sensitive languages, and these are type 0 languages. Right? Got my point? The grammars that generate the regular languages are
Sir, you're on mute, sir. Sir, you're on mute.
how long am I mute?
Sir, just now, sir, just now.
Okay. Something happened. Sorry. Can you see my board?
Yes,
Can you
sir,
see
yes.
my board? Yeah.
Yes, sir, yes.
Okay. Yeah. So I define a hierarchy like this. I will go into details that why this is a hierarchy. I'll go just stay with me. I define a hierarchy like this, that okay, these are regular languages, these are context free languages, these are context sensitive languages. The grammars that generate these languages are called context sensitive grammars, and the grammars that generate T0 languages are called phrase structure grammars. No need to worry about the names right now. What I mean to say is that that how I classify these languages is exactly same as how I classify these grammars. Got my point? So what I mean is that that these grammars have these grammars can be classified like this, that what should be the base of classification? What should be the base of classification? The base of classification can be justified by restrictions. So by restrictions on alpha or beta. So grammar in the most general form, just look into this picture and forget this picture for now, right? So grammar in its most general form are the set of productions, right? Which are of the form alpha is getting reduced to beta. So there can be many alphas getting reduced to many more betas, right? So the set of productions actually is the grammar. Having said this, what you can say is that we classify this hierarchy. We classify this hierarchy of regular grammars, and then okay, let's classify in a different mode altogether. What I do is, let us classify with a pyramid like this, right? Let us classify with a pyramid like this, and we say that okay, this is regular grammars, this is context free grammars, this is context sensitive grammars, and this is type 0 grammars. And why I draw a pyramid like this, the width of the pyramid increases with increasing restrictions. Now what we mean by restriction, we only have alpha goes to beta as one of our key candidates for defining grammars. So what exactly we mean by restriction is how alphas and betas are designed, right? So if we say that regular grammars are the most restricted, the increasing restriction, most restricted, we say that okay, alpha mod alpha is equal to 1, alpha mod alpha is always less than equal to mod beta, and beta is, this is how it should look like, series of terminals if there are no non-terminals, or beta is, I am denoting this with the or beta is a series of terminals followed by a non-terminal, if at all you have a non-terminal on the right hand side, right? So by this I mean that beta, this is restriction put on beta. You are trying to dictate how beta should look like. In case of context free grammar, since it is above the hierarchy of regular grammars, it should be less restricted, right? And that less restriction is meant by that okay, mod alpha is equal to 1 and beta is free. So there is lesser restriction on beta. So regular grammars, beta is more restricted. There you have no restriction on beta. In case of context sensitive grammars, the 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 grammars that are even less restrictive than context free grammars, you say that mod alpha is less than equal to mod beta, but mod alpha need not be 1. So here you put a restriction on how alpha should behave. You say that alpha should be 1 exactly. Here also that restriction is percolated down, right? Mod alpha is 1 here also. But in case of context sensitive grammars, you say that mod alpha is less than equal to mod beta. That should be there, but mod alpha need not be equal to 1. So the left hand side need not be equal to 1. And for T0 type of grammars, there is no restriction either on alpha or beta. Did you get what I'm trying to say? Yes or no?
Sir, could you go
Yes
back
or
to the
no?
pyramid once, sir?
Yeah, I am drawing the slide once more. No problem. Feel free to ask me, right? I am drawing the slide once more. I am drawing a pyramid to explain what exactly we mean by restrictions, and the restrictions go downwards. So increasing restrictions. Now my argument is, if all grammars are denoted simply by alpha goes to beta, where alpha beta are elements from V union T star, so we have to define restriction in terms of alpha and beta, how alphas and betas look like, right? So increasing restrictions arrow is downwards. So if we say that the regular grammar is the most restricted grammar, it should be here. If we say that the context free grammar is less restrictive than regular grammar, it should be above regular grammars in this pyramid, right? if we say that there is another grammar called context sensitive grammar that is even less restrictive than context free grammar, it should be here. And if we say that there is another grammar called T0, T0 grammar that is least restrictive, that should be the topmost block of the pyramid. This much you understand, right, from logic. Now what I try to say is that if we say that this is increasing restrictions on grammar rules, and if we say that grammar rules only have the form alpha goes to beta, where alpha and beta are strings from V union T star, then we have to define restrictions in terms of alpha and beta. That means restriction, if restriction is a function, it should be a function of alpha and beta only. You have nothing else to define restriction. Do you agree? Do you agree? Do you
Yes,
agree
sir.
with me? Yes or no? Yes. So let me repeat once more. So grammar rules are only of the form some alpha getting reduced to some beta, or some alpha getting expanded to some beta. Reduction or expansion are different terms, but used in the same context of grammars. It may have different aspects in case of machines. I'll show you how. But for grammars, you say that okay, grammar rules are nothing but alpha, some alpha getting reduced to some beta in due course of time, giving birth to strings. That is what you mean. So S goes to 0 S1, applying n number of times, you get 0 n 1 n. So you get a string of n zeros and n ones. That is what you get, right? Applying S goes to 0 S1 n number of times. And lastly, you applying S goes to epsilon. So after all, it is alpha arrow beta. So if we have to define restrictions, if we have to define the hierarchy, that needs to be based on some logic. And the logic to define a hierarchy of such grammars is called restrictions. And what we mean by restrictions is how we impose restriction on alpha and how we impose restriction on beta. So having said that T0 is a type of grammar that has no restrictions, we say that alpha and beta have no restriction or can be anything. Alpha beta can be anything. Now you impose a bit of restriction to this anything clause, and you say that the next grammar called context sensitive grammar, according to this hierarchy that we have designed, is more restrictive than T0. How to define that restriction? Remember, if you have to define restriction at all, that should be defined in terms of alphas and betas only. So you define restriction of CSG with respect to T0 with something like you say that, okay, here alpha and beta can be anything. Here I say, in case of CSG, I say that, okay, alpha, I put a restriction on alpha, that alpha should be less than equal to beta. Mod alpha, the left hand side of any string should be any production, left hand side string of any production should be less than equal to the right hand side of any production. You impose a restriction. Here there was no restriction. So it means with the knowledge of these two, it means, so now we have the knowledge of these two, it means that here mod alpha can be greater than equal to mod beta also, right? But we are not going to write that. We are going to write in a more sophisticated formal way that alpha beta can be anything. So anything is most important. Here I impose a restriction, I add little bit of salt to the food, and we say that mod alpha should be less than equal to mod beta. That is what we say. Here we add one more restriction that, okay, mod alpha is less than equal to mod beta, that should be okay. Additionally, I say that mod alpha should be equal to 1. Not only that it is less, it should be exactly 1. But beta is free here. Nobody is talking about beta. Beta is free here also. And here, in case of regular grammars, which is the most restrictive one, increasing restrictions, you remember, right? This is the most restrictive one. You say that mod alpha is less than equal to mod beta. You take these restrictions, percolate down, no problem. Mod alpha is equal to 1, no problem. But here also I dictate terms in how beta should be looking like, how the right hand side of production should be looking like. And we say that right hand side of production should be a finite series of terminals if you don't have a non-terminal, or if you have a non-terminal, it should be the rightmost symbol. It should be rightmost symbol. Now, does it justify? Yes or no? Is my explanation logical and acceptable to you?
Yes, sir. Yes, sir.
A bit of confusion, right? In your yes, it's not a very confident yes.
No, sir. No, sir. I'm confident. I didn't understand it last time, sir, but now I understood it, sir.
You understood? Okay. What about others? This is a very important concept. You need to understand, right? So I
Yes,
repeat.
sir.
Yeah, I repeat in two sentences. What I say is, having said that, grammar rules are very simple things like some string alpha getting reduced to some string beta. That is a basic concept where alpha, beta are strings from V union T star. That means alpha, betas are strings that contain both non-terminals and terminals. Example, S goes to 0 S1. Here S is a string that contains only one terminal V. Here, right hand side, it's a string that contains terminals 0 followed by a non-terminal S followed by a terminal 1. So this is here alpha is S and beta is 0 S1. Any problem? No problem. But what I mean is, if having said that, grammar rules are only of this form. Now, if you want to classify grammars according to their structures, that is what I tried taking examples of any number of zeros and equal number of any number of zeros followed by any number of ones, and on the contrary, equal number of zeros followed by equal number of ones. Why I took that example? Because you have a pre-knowledge that any number of zeros and any number of ones is regular, and you also have the knowledge that equal number of zeros followed by equal number of ones is not regular. So I took those examples, right? And I didn't take any other example. I took those examples so that things become very clear to you. So, having said that, grammar rules are only such rules, and immediately finding that 0M 1N is a regular language, whereas 0N 1N is a non-regular language, and with the concept of VTPS grammar, we found a regular grammar for this, and with the concept of this VTPS structure of writing grammars, we found a non-regular grammar for this, right? We found a non-regular grammar for this also. S goes to 0 S1, and here we found a regular grammar for this. Now I tried to point to the fact what is the difference between these two. You say that this is a regular grammar that generates this regular language, and this is a non-regular grammar that generates this non-regular language. So what should be the difference in their structure? The difference in their structure is simply put that the regular grammar has productions that has right hand sides exactly these. No other right hand sides are allowed. But the non-regular grammar, in our case, I have named it as context free grammars. I have not yet explained why it is called context free. Let that I have given a proper noun. I have given a name. Let this non-regular grammar be named as context free grammar. If it is so, then we can see that in our case, that S goes to 0 S1 for the equal zeros and equal n's equal ones case, it follows that the right hand side has no such restriction that beta should look like this or beta should look like this. Beta is free. Now, with this concept, let us go back to the grammars again to match what we are talking, right? So this is what I mean. See, I come back here to the regular language and the non-regular language. So this was the regular language, this was the regular language, and this was the regular grammar. I transform the grammar so that all the rules conform to some general structure, and these are the rules where each rule is of the form S goes to 0s, S 0s is the right hand side of this production, and since 0s is the right hand side, we have S the non-terminal on as the rightmost symbol. No problem. Here also we have this. Here also we have this. So here we conform to the case that beta is series of terminals followed by non-terminal. And we have also productions like S goes to 1, A goes to 1, and this conform to this is how beta look like. And in this case of non-regular language, thus the 0n 1n case, this was the 0n 1n case. In this 0n 1n case, you had a rule like this: S goes to 0, S1, right? And here we see that there is no restriction that S is on the right hand side of this production rule. That means beta is 0 S1, and there is no such restriction that since beta is 0 S1, S should be on the right as the rightmost symbol. No, nobody has put any restriction on how beta looks like. So with this knowledge, we can say that, okay, our non-regular language, the non-regular grammar, it belongs to any one of these, right? Because the beta is free. Here also beta is free. Here also beta is free. Here also beta is free. So it belongs anywhere here, right? Got my point? But I named it as context-free grammar. Why? Because mod alpha is 1. In our case, in the equality case, we had S goes to 0 S1 and S goes to epsilon. In both this is alpha 1 goes to beta 1, this one, and this one is alpha 2 goes to beta 2. So we had two alpha arrow betas. One is S goes to 0 S1 and one is S goes to epsilon. And in both of these, both alpha 1 and alpha 2 are mod alpha 1 and mod alpha 2 are 1. So having defined rules in a formal way like this, that mod alpha should be 1, we can say that, okay, our non-regular grammar of 0 and 1n is nothing but a context-free grammar. But if we go by the English term called context-free, we should always have something called contextual or context-sensitive. So if you are not put behind bars, you will never have the feeling of freedom. It's contrast, right? If you don't have darkness, there is no value for light. Similarly, if you can't define something like context sensitive, there is no meaning of naming this portion as context free. And you say that this is context free because there exists something called context sensitive. Otherwise, you could have given a different name to that, right? You could have named it non-regular 1. You could have named this non-regular 2. You could have named this non-regular 3. What's in a name? You could have named this. But that you have named that this portion is called context free, it means that, okay, we had something called context sensitive, or we can define something called context sensitive. And in that context, anything that is not context sensitive, but is also not T0 is context free. That is how you define. Got my point? Okay. Now, let us end today's class. What is the time? Let us end today's class with one more example. Now, there is a regular expression. Forget about what I was talking before this. Clear up your brains. Let there be a regular expression: 0 star, 1 star, 2 star. Can you remember the NFA that you built for this epsilon NFA? Do you remember? Do you remember? Yes or no? Or you forgot? Hello?
Yes, sir. Sir, an epsilon NFA for this.
0 star, 1 star, 2 star, you forgot? 0 star, 1 star.
One star. Yes, sir, yes, sir, yes, sir. Now I remember, sir.
Now you remember? You have such a volatile memory, more volatile than me, right? So it confirms, your knowledge confirms that this is a regular language. This is a regular expression for this. Let me replace 0 by ABC to make it more general, right? So what I mean is, let there be a language represented by the regular expression representing this language is A star, B star, C star. So you are sure that this is a regular expression, and so this is a regular language, and you can perceive epsilon NF for this. So all these three things say that you are sure that this is a regular language. And now that you know, let us come back. Now that you know that, okay, regular grammars should have this structure, that left hand side is 1 and right hand side should be having only terminals or terminals followed by non-terminals. If you have non-terminals, they should be on the rightmost, they should occur as the rightmost symbol. So with this knowledge, if I ask you to design a regular grammar for this language, what should you do? You can simply use your concept of this finite automation structure and join the states and define. For example, I internally think of generating these small a's, these terminal strings, small a's with a non-terminal capital A. I think of generating the small b's with a non-terminal capital B, and think of generating small c's with a non-terminal capital C. Very simple. I have a start symbol and I go to A to generate any number of a's. Done. Then from this state to generate any number of a's, from this state, say, either I generate more a's by the tail recursion, A goes to small a, this capital A will, the capital A on the right hand side, you will be again generating a's, right? And please turn off your microphones. And also I should have a route that will take me from this state capital A to capital B, right? So I'll directly go to this state capital B, which will be responsible for generating the B's. And after you go to B, you should be generating more small B's. And from the state capital B, you should be going to a state called capital C to generate C's. And in capital C, you generate small c's, more small c's, right? Or you terminate with a small c, right? And you terminate this s with an epsilon so that you can accept epsilon. Sleep over and accept epsilon, right? A star, B star, C star always has epsilon as a minimal string. I hope you remember my concepts. So this is a grammar. Now you can see that each right hand side is, if you have a non-terminal on the right hand side, it is the rightmost symbol. No question about that. Or you have simple productions like this. Capital C goes to small c. Now remember, small a, small b, small c are elements of sigma. Capital A, capital B, capital C are your non-terminals. So in your grammar, your non-terminals are S, A, B, C, and your terminals are A, B, C. This is a set of production rules that conform to the right hand side. Each right hand side has, if the right hand side has non-terminals, they are the rightmost symbol. It is true here, 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 it is true here. Or the right hand side can be a terminal, right? So capital C goes to small c is such a production. So this is your regular grammar, right? And if you can visualize, so everything is visualization, right? If you can visualize this NFA, epsilon NFA, I have done nothing other than naming these states as your non-terminals, capital A, capital B, capital C. So capital A is responsible for generating more A's with a tail recursion, right? With a rightmost recursion. Then A slips over an epsilon and goes to state B. A slips over an epsilon and goes to state B. In B, you generate more B's, right? Then after generation of the required number of B's, you slip to state C. This is like what you do. For example, you have a string like this, 2 zeros, a single one, and 3 twos, right? This is a simple string. So what do? You start at S, S goes to, go through the production, S goes to A, right? S goes to A, then A goes to A, then again I apply this A goes to A, give a bracket so that you understand, and now I will erase the bracket, hoping that you understood. And now what I'll do is, again I'll apply this A. So I'm applying this production 3 times to generate 3 A's. Very simple. Okay, let it be 3 zeros since I've already applied 3 times. Sorry, I will be representing this with A's and B's. A, a single B, and 2 C's, for example. So I have applied this, and then I will apply A arrow B, and I will go to triple A B. Then I will apply B arrow small b capital B, small b capital B. I change this B to small b capital B. Then I apply B goes to C because I have a single B. B goes to C. So I have triple A B capital C. Then I apply triple A B. I will apply C goes to small c capital C, small c capital C. How many C's you have? 2 C's. So I have to apply 2 times. And then I apply capital C goes to small c capital C. Or you have 2 C's. So let us apply capital C goes to small c to terminate. Right? So we'll not apply this again. We'll apply the other production to terminate. So I will apply simply capital C goes to small c and terminate. So I have 3 A's, 1 B, and 2 C's. So the string is generated by application of productions. So what production do I use? A goes to small a capital A. Then again I use the same production. A goes to small a capital A and replace this A with AA. Again I replace this AA, this capital A with AA. Then I apply A goes to B. The rest of the string remains same. A is replaced with a B. And then I apply B goes to small b capital B, and I replace this B with a BB. Then I apply B goes to C and replace this B with a C. And then I apply C goes to small c capital C and replace this C with a small c capital C. Then I apply capital C goes to small c and replace this C with a small c. Done. And this is a string that we'll end up with. This is the same string that you would end up with if you follow the finite automata model. Now, the rationale behind taking this example is again to be able to show you the whole picture, right? So that you can visualize things, so that you don't complicate things, so that you don't try to memorize grammars. You should be able to visualize things in front of your eyes, in your thoughts. Does it make sense? No reply from anybody?
Yes,
Sir,
sir.
could you just scroll down to the last transformation just once, sir? I just wanted to check one thing, sir. It's not about.
Yes. Check as many times as you can
Sir,
and confirm that it's okay with you,
sir,
because that would make, yeah, bolo.
s-
Yes.
sir, sir, in the grammar, when C goes to CC,
Where?
sir, in the grammar, production rule, sir.
Yes. Yeah, production rule. Where? This one?
Sir,
Which one?
sir, yes, yes, sir. When C goes to a small c, capital C, and C goes to C,
Yeah.
sir,
This
can
is
we
for
say,
terminating. This is for
yes, sir,
terminating.
sir, yes, sir, can we use epsilon for terminating?
Yeah,
I'm asking
of
this.
course, you can use. Of course.
Yes, sir.
Of
Okay, sir.
course. Either you use this C, either you use this C, or you can use an epsilon. Very good. I'm very happy. Right. But since, why did I use a small c? So that it conforms more to this description of beta, where I have told that beta should be terminals only or terminals followed by non-terminals. Now I can show you that capital C goes to epsilon. I can reduce this to something like this is same as capital C goes to C, right? Got my point?
Yes, sir. Yes, sir.
Yeah,
Got it.
yeah. And in fact what you can do is, in fact, capital you can apply this. You can, for example, here you can apply. So if you have capital C goes to epsilon, what you have to do is for generating two C's, you have to apply C goes to small c capital C again, right? Small c capital C, and then apply capital C goes to epsilon. So you have triple A B double C. Got it?
Yes,
Clear?
sir. Got it.
Yes. So can you see? Can you relate these things that this is such a simple way of defining the grammar directly from your automation, right? Now, what does the concept like? The concept is when I was talking about in the automated classes, I was talking about the I was giving maximum stress in the fact that you should be conceptualizing the functions of states. So here I have just conceptualized that let there be a state A responsible for generating A's, let there be a state B responsible for generating B's, let there be a state C responsible for generating C's. I've done a very simple thing, and I have put this whole concept in this automata and found that okay, this is exactly the same way the finite automator works. And I have just, you can say that I have just, you can say in this particular example, this is just a code of the automata. This grammar is nothing but the code of the finite automata. In that way, you can say this. This is just a reflection of your automata. Isn't it beautiful? Yes or no? Yes or no?
Yes,
No
sir.
answer from anybody. Yes? Okay.
Yes, sir.
Okay. So let us end today's class with another example. Just a very simple example, just to test you whether you are thinking. Now forget about regulars, non-regulars. Just concentrate on VTPS and concentrate on the rules that I just talked about. Right? And give me a grammar for the language of palindromes. Let it belong from sigma star, where sigma is 0, 1. I've made things very simple. So what's a palindrome, by the way? What is a palindrome?
So which is uh, it's the same even in the reverse order.
So this is a palindrome, right?
Yes, sir.
Yes, do you agree?
Yes, sir.
Okay. Is epsilon a palindrome?
Yes, sir.
Okay, thank you. I'm happy that you are conceptualizing epsilon. Okay, is 0, 1, 0 a palindrome? Yes.
Yes, sir.
Is
Yes, sir.
Yes.
yes, 1, 0, 1 is a palindrome, right? Okay,
Yes, sir.
right. Is single 0 a palindrome?
Yes, sir.
Yes. Single 1 a palindrome? Yes.
Yes, sir.
No problem.
Yes, sir.
So can you define a grammar for this?
Sir,
Yes.
sir, we can define like production rule S goes to 0 and S goes to 1.
Then
Then S goes to 0 S1. So 0 S1. Yeah.
no, no, that's the wrong concept. S goes to 0, S1 will not give you, if you have something like S goes to
Sir,
0,
0 S0. Sorry, sir. Sorry, 0
0
S0 and 1 S1. 0 S0 and 1 S1.
Yes, sir.
and S goes to epsilon, right?
Yes, sir.
Yeah.
Now today I'm so happy with you guys. Very good. So that proves that I was able to translate the concept to you. That proves that I was successful in uh, translating the thoughts, the ideas, and the concepts and the rules. Right? I'm very happy. So that you conceptualize that this gives a palindrome. Ends today's class, and I'm very happy with you. Thank you. I will take class on Tuesday, but I will not be able to take class on Thursday. So next week classes will be on Tuesday and Friday. Friday I will take class from 5 p.m. and Tuesday it will be on 3:45. Right? Got it? So please go through books and try to concentrate on what I was talking about. Shall I end or shall you do another grammar? Okay, let me give you a assignment and then I will. Okay, give me a grammar for 0n, 1n, 2n. Give me a grammar for this. A grammar that generates this. You hear? Can you hear me?
Yes, sir. Yes, sir.
Yes. Give a grammar for this language. Let us do a brainstorming, right? I'll wait for 5 minutes. Just think what to do. Before thinking what to do, try to visualize that what sort of grammar is this given the pyramid, what sort of grammar is this, or what are the main
So this is
characteristic behind this
non-regular,
grammar?
sir. Sir,
Okay,
non-regular.
yeah, that's very good. This is non-regular based on the concept that if 0 and 1n is non-regular, so should be 0 and 1 and 2n, right? That's very good. This is non-regular. And how does it differ? Okay, I'll give you a clue. How does it differ from 0 and 1n? How does it differ? So L1 is 0 and 1 and 2n, L2 is 0 and 1n. Now I'm asking how L1 differs from L2. Just think and answer me.
Sir, it's one extra state, sir, with a loop.
Now I will like to argue with you that does a extra state add more complexity to your machine?
No, sir. No, sir. No, sir.
Okay. Let me put the question with more formal and better English. Does adding a state change the necessarily can change the character of your machine? No, right?
No, sir.
Yeah. So it's not about an additional state. It's about an additional characteristic. Of course, it's about an additional state, but it's more about an additional characteristic, right? And what is that characteristic? Please try to dig into that. You get the answer, and once you get the answer, we can have a grammar. Right? Think for 2 minutes. Just give me a break of 1 minute. I need to check something, right? Very urgent. Just think. 1 minute. I'm coming back. Yes. Do you have an answer? Hello? Are you there? Hello,
Yes, sir, we are here.
you are there. Okay. So, did you ask yourself why they are different? Okay, what makes this language? What makes this language non-regular? What special characteristic makes this language non-regular? Equality, right?
Yes,
Of
sir.
zeros and ones. Because equality of zeros and ones has something to do with counting zeros and then adding ones. Exactly the same number. You have to count how many zeros because you have to add exactly that many number of ones. So this equality of zeros and ones was making this language non-regular. Right? Okay, let us come back to a machines. A regular language is accepted by a finite automata that has a tape and a finite control. I represent the finite control with a del, the transition function. Simple. Done. It has a tape and your tape head only moves towards the right by scanning one symbol at a time and applying one del at a time. Agreed? This was a finite automata model conceptually. You didn't have memory. You didn't have a structure that says, okay, I have seen only 3 zeros. Did you have? Did you have a memory-based implementation in finite automata? No, you
No,
just
sir.
had an input tape. You just had an input tape and a transition function that says, okay, if I see a zero, what to do? If I see a one, what to do? But in no way can you remember how many zeros you have seen. In this case, you have to remember how many zeros you have seen, n zeros you have seen. So what you need is immediately you need something called, there is a transition function that should scan and move right as usual, but you should have an additional memory also, a stack. And the algorithm is, if I see a zero, I push a zero. If I see a zero, I push another zero. If I see a one, what I do? I pop a zero. If I see another one, I pop another zero. So if I have exactly two ones followed by two zeros, the stack becomes empty. And you accept by when the stack is empty. Make sense? Make sense? Yes or no? How do you count? I'm
Yes,
talking
sir.
about the counting algorithm. Very simple counting algorithm. How do you count? So you need to push, you need to store the number of zeros that you see somewhere, right? There is a storage. You store the zeros as you see them. And then the algorithm says that, okay, if I see a first one, I'll not store any more zeros or ones. Rather, I will take out the zeros that I had stored. So you mark the end of the stack with a dollar sign, a special sign, and for two zeros you do two pushes. You see a zero, you push it. You see another zero, you push it. You see a one that is not zero, you pop this zero out of the stack. You see another one, okay, you pop this zero out of the stack. And if this was the string, really if this was the string, you accept because the stack becomes empty. Or the end of the stack symbol dollar is exposed. That's the algorithm. So what's the algorithm? Simple. Push zeros until you see a one. Pop zeros for each one that you see. If the stack is empty and the string is exhausted, you accept. Agreed? Yes or no? I'm talking very simple things. Yes or no?
Yes. Yes, sir. Yes, sir.
Yes. Now this memory was absent in your finite automata model. That is what makes 0 and 1 and non-regular. Right? Now come back to this problem. 0n, 1n, 2n. Can you do this with this simple memory mechanism? Can you do this? For example, you say that okay, I have an input and I have a memory. I see zeros and I push the zeros. I see a 1 and I pop the zeros. Now what about the 2's? What to do? The stack has become empty. You have lost the count. Agreed? Yes or no?
Yes, sir.
Yes, sir.
Yes. The stack has become empty. How to match the 2's with the zeros and ones? I repeat once more. So this was your finite control. This was your del, and the del was controlling the stack also, the push and pop operations. So the algorithm is you see a 0 and push the zeros until you see a 1. So you push 2 zeros in this example string. Now once you see a 1, you pop, right? You pop, you see a 1 and you pop 1 0. You see another 1 and you pop another 0. Done. Now your stack suddenly becomes empty. How to deal with the 2's? $1,000,000 question. The
Sir,
stack has become empty. Yes.
sir, can we do like that? We add 0 and 1s until we see 2, and when we see 2, we will pop 0 and 1.
Repeat once more.
Sir, we will be go adding 0 and 1s to the stack, and when we see a 2, we will exactly pop a 1 and 1 0.
So you will go on pushing, right? So you push 2 zeros and you push 2 ones.
Yes, sir.
You defer the popping, right? And you find a 2. You
Yes, sir.
pop a 1, right? You pop a 1, right?
Yes, sir.
You find another 2. You pop another 1. And your algorithm ends if the top of the stack is a 0, right?
Okay, so got there will be problem.
Is it? Are you saying this?
No, sir.
Yes, you are not saying this because what if I change the string to have 3 zeros, 2 ones, and 2 twos? So you have 3 zeros pushed, you have 2 ones pushed. So even if the number of ones and twos are same, 2 ones and 2 twos, it means that for each 2 you pop a 1. Zero is what is exposed, but you have 3 zeros. Your language has all zeros, ones, and twos to be all same. So your design accepts a string like triple zeros, 2 ones, and 2 twos. That should not be the case. You are accepting this, right? With your algorithm. That should not be the case. Agreed? Yes or no?
Yes, sir.
Done. So let us go with a more simplistic way. So you have zeros, ones. Your head only moves right, like this, right? You have finite control del, and that del also controls the stack. Now what I do is let me add another stack. What I do is for zeros, I push the zeros in stack number 1. When I see the first one, I pop zeros from this stack and push it in this stack. Or I can pop a 0 and push the 1, no problem. The same thing. The push the 1 that I see a 1, I pop this 0 and push a 1. I see another 1, I pop this 0 and push another 1. So only if the zeros and ones are same, only then my stack will, the stack number 1 will be empty and stack number 2 will contain the same number of ones. So you assure the same number of zeros and same number of ones. Now once you see a 2, you pop the ones, you go on popping. So if you see two twos, there are exactly two pops, and both the stacks are empty. So both the stacks are empty. Guarantees both the stacks as well as the string is exhausted. This is the right hand marker of the string. So both the stacks are empty and the string is exhausted. Guarantees that you have 0n, 1n, 2n. Does it make sense?
Yes, sir.
Yes? Yes or no?
Yes. Yes,
Yes.
yes, sir.
Yes. So now your del, that means the transition function of this machine. Let this be a machine, right? I have not named the machine here, but this is of course not a finite automata because it has memory. So this machine has control of both the stacks. What is the algorithm? Algorithm is very simple. Push zeros in stack 1 until you see a 1. Right? Pop zeros and push ones in stack number 2 until you see a 2. If after step 2 stack 1 is empty, proceed. Step number 4, for each 2 pop a 1 of stack number 2 and continue reading. Step number 5, if stack 2 is empty and the string is exhausted, you accept. Does it make sense? Yes or no?
What are the last two words of step number 4, sir?
Okay. You cannot see, right? Okay.
Yes, sir.
For each 2, pop a 1. Pop a 1.
Of
For
H2
each
and
2, for each 2 that you see, pop a 1. Pop a single 1. Now it is okay. Of stack 2 and continue reading. Reading the string. For each 2 that you see, you pop a 1 from stack number 2. That is what I mean. For each 2 that you see, pop a single 1 from S2 and continue reading. Right? Now continue reading. So if they are really same, stack 2 should be empty and this string should be end. Right? So if S2 is empty and the string is exhausted, you accept. Agreed? Yes or no?
yes, sir.
Done?
Yes,
Right?
sir.
That is what makes 0n 1n a different problem than 0n 1n 2n in the most general form. Because it's not about adding a state, right? It's not about adding another stack, but it's about the control of the two stacks at the same time. Got my point? It's not about additional memory only. It's about the additional control. Got the point? One may argue that if I have a stack, I can have another stack. No, it's not like that. It's not about having an extra stack only. it's also about, and it's more about having this extra control together. Got my point? Now, this is just for your information that the 0 and 1 in case, this 0 and 1 in case was not your finite automata model. Without a memory cannot solve this, and that's why it is non-regular. And the model that solves this is called, the model that I have drawn here, a finite automata with a stack and a stack control mechanism. That means your algorithm is called push down automata. Just know this, what is push down automata, and we'll continue with in the next class. Okay, any questions you have? Everything clear? Yes.
Yes, sir. Yes,
I
sir.
think everything should be very clear, right? Why other people are not interacting with me, and nobody is interacting with me? Nobody ever talks with me. Only Prajat and Basu and some more people only talk with me. Other people don't like me, I think. Okay, that ends today's class. See you on Tuesday at 3:45 p.m. Okay?
Thank you.
Yeah, bye.
Thanks,
Thank
sir.
you, sir.
Hello.